Good day and welcome back for the fourth and final part of our discussion on areas enclosed between curves. So back to this standard question we've been investigating. Find the area enclosed between the curves given by x equals 2y squared and x equals 4 plus y squared. And note, this is a scenario that we left off with in the previous video. We have two functions of y. Our first step towards determining this enclosed area is sketching the graphs of these functions and seeing if we can identify that region enclosed between them. So both x equals 2y squared and x equals 4 plus y squared are going to be parabolas opening in the positive x direction, so opening to the right. X equals 2y squared is going to have a vertex sitting at the origin, and because of the 2y squared versus just a 1y squared, it's going to be a bit narrower as a parabola. So roughly speaking, it's going to look something along these lines. So in black, we have the graph of x equals 2y squared. Similarly, x equals 4 plus y squared is going to be a parabola with a vertex sitting on the x-axis at 4 and opening in that positive direction, but it's going to be a bit wider than x equals 2y squared. So in blue, we have x equals 4 plus y squared. And remember, sketching these functions of y is certainly an acquired skill, something that we need to practice. But like anything else we encounter, the more we practice, the more efficient we are going to become. So I'm just erasing a bit of these curves to create some space. And now let's think about our next step. We have this nice enclosed region A, whose area we would like to calculate. Because we are thinking of these in terms of functions of y, what we need to know would be the y coordinates of these points of intersection. Now note, I don't care at all what the x coordinate is. I only care about the y coordinate. Sitting these two curves equal to each other, 2y squared is equal to 4 plus y squared. So subtract y squared from both sides and solve for y. Plus or minus the square root of 4 is plus or minus 2. The y coordinate in that upper point of intersection is 2, and the bottom point of intersection is minus 2. And that will give us our limits of integration to set up the integral representing this enclosed area. So A is the definite integral over how the y values are varying, minus 2 to 2. What we integrate is the larger curve minus the smaller. Remember, larger is in terms of x here, so further to the right is the bigger curve, further to the left is the smaller. So we would integrate 4 plus y squared minus 2y squared. And this is the new, and probably what we could all agree upon, the most difficult part of this problem. Getting the picture drawn, finding the points of intersection, setting up this definite integral to evaluate. So let's go ahead and evaluate it. Simplifying the integrand, we are integrating 4 minus y squared, and then evaluating this definite integral with the fundamental theorem of calculus, we simply anti-differentiate term by term, and we need to evaluate from minus 2 to 2. So replace each y with a 2, minus sign, replace each y with a minus 2. And we can leave it exactly in this form. The quantity that we get back is going to represent this enclosed area. So we now have two examples remaining, and this is just to get some extra practice. In both of these examples, a region bounded by curves is described, and what we are asked to do is to sketch that region of integration and then set up, but do not evaluate, a definite integral that represents the enclosed area. And this is the perfect time for you all to get some practice in. So what I would ask you to do is pause the video and give yourself, a solid 7, 8, 10 minutes and see if you can sketch these regions, set up the definite integrals. And hopefully at this point you have done so. I'm going to go ahead and just sketch the pictures and work through these a bit more quickly than the previous examples. So the two curves of interest in this first example would be y equals the square root of x and x equals 1/2 x. That would be a line going through the origin with slope 1/2. And we want to find the area enclosed between these two curves and x equals 9. So let's pretend x equals 9 is about here. So looking at these two curves, up to x equals 9, we see two distinct enclosed regions that we need to worry about. We have this region enclosed to the left where the square root of x is the larger curve, and another region enclosed to the right where y equals 1/2 x is the larger curve. So what we need to do is figure out what is the x coordinate of this point of intersection. That will allow us to set up the integrals. That is, when is 1/2 x equal to the square root of x? To solve, we'll square both sides. So 1/4 x squared is x. And our goal in this case is to solve for any values of x that satisfy this equation. And just from past experience, we may have noted it's preferable not to have these fractional coefficients. So I'm going to go ahead and multiply by 4 to write this as x squared is equal to 4x. And now it's maybe a bit simpler. X squared minus 4x equals 0. Both terms involve a x, which we can factor out. And those intersections would correspond to x equals 0 and x equals 4. Exactly what we see in our picture. Now for the definite integral. We need two of them. One from 0 to 4 and one from 4 to 9. On that interval from 0 to 4, we take the larger function and we subtract away the smaller. Similarly, on the interval from 4 to 9, we take the larger function and we subtract away the smaller. And this is where I would stop the problem if I was asked to sit up but do not evaluate. If you would like some extra integration practice, I'm going to note if you continue on and evaluate, your answer would simplify down to be 59/12. For the second example on this final page, we would like to once again set up but do not evaluate an integral that represents the area of the region enclosed by the parabolas, hint, x equals 1 minus y squared and x equals y squared minus 1. And once again, my hint to sketch these parabolas is to really think of those defining characteristics. As a function of y and a parabola, is it going to open to the right or to the left? And what are those y-intercepts going to be? So in this case, let's just go ahead and factor each one of these to get those y-intercepts. So 1 minus y squared is a difference of squares, 1 minus y, 1 plus y. Because of the minus in front of that leading coefficient y squared, it's a parabola opening in the negative direction, i.e. to the left, with y-intercepts plus and minus 1. So roughly speaking, we have 1 and minus 1 as our intercepts, and it's a parabola opening to the left. So in blue, we have x equals 1 minus y squared. By a similar analysis, if we look at y squared minus 1, that's a parabola opening to the right, and if we factor it, we'd have y minus 1, y plus 1. So it has the same roots of plus or minus 1, but now it just opens to the right. So in black, we have the graph of y squared minus 1, and we see this nice enclosed area, which we'll call A. So this enclosed area is a definite integral over how the y values vary. And by our sit-up, we immediately see the y coordinates of those 2 points of intersection. Y equals +1 and -1. So we don't have to do a separate algebra problem in this case. But note, you certainly could, and if you did, you would get y equals ±1. So we integrate over how those y values vary. We integrate the larger function minus the smaller function. And this is where I would stop for the sit-up. I would prefer not to simplify it with the sit-up because then I can clearly see the thought process of a larger curve minus a smaller curve. If you would like some additional integration practice, always a good idea. What you would get if you evaluated this is 8/3. This ends our discussion on areas enclosed between curves. In our next topic, we are going to step everything up a dimension, in a sense, to talk about volumes, specifically focusing in on things called solids of revolution. So stay tuned and take care.